You know, it's pretty amazing how something as abstract as math can perfectly describe something so, well, real, like a weight bouncing on a spring. Today, that's exactly what we're going to dive into, using the powerful language of differential equations to translate real-world vibrations into some really elegant formulas.
So here's our game plan. We're going to start by building a simple model. See how things would work in a perfect, frictionless world. Then we'll get real and add stuff like damping. We'll explore the different ways a system can settle down. And finally, we'll connect it all back to why this is so important in the real world. All right, let's get right into it. The very first thing we need to do is take a physical system, in this case our trusty mass on a spring, and figure out how to translate its behavior into the language of math.
Right, so this is the big question, isn't it? How do we possibly take this physical motion, this constant back and forth bouncing, and boil it all down into a single equation? Well, it all starts with figuring out what forces are actually at work here. Okay, so picture this. You've got a weight, let's call its mass m, and it's just hanging from a spring. Now, if you pull it down and let go, what happens? The spring tries to pull it right back up, right? That pull is what we call the restoring force. And according to something called Hooke's law, that force is directly proportional to how far you stretched it. That's the displacement, x. The k in there, that's just a constant that tells us how stiff the spring is. A bigger k means a stiffer spring.
Okay, with that, we can write down our very first equation. Now, I know this might look a little scary, but trust me, it's simpler than it looks. Let's just break it down. That first part, m times that d squared x over dt squared thing, that's just a fancy way of writing Newton's second law. Force equals mass times acceleration. Seriously, all d squared x over dt squared means is the acceleration of our mass. Simple. And the second part, kx, well, that's just the spring's restoring force we were just talking about. So in a totally perfect world, these are the only two forces, and they cancel each other out perfectly.
So now that we have our ideal equation, what happens when we solve it? We're talking about a perfect system here. No friction, no air resistance, absolutely nothing to slow our little spring down.
What we get is something called simple harmonic motion. And honestly, it's the purest, most perfect kind of vibration you can imagine. It's this beautiful, repeating wave that, at least mathematically, would just keep bouncing up and down forever and ever, without losing even a tiny bit of energy.
And this visual really shows that perfection, doesn't it? Take a look. See how every single peak and every single valley hits the exact same height? That constant height is what we call the amplitude. And in this perfect little world, it never, ever changes. It's like a visual fingerprint for a system that has zero energy loss.
But yeah, we all know we don't live in a perfect world. Any real spring you've ever seen will eventually stop bouncing. So let's get real. It's time to add a new ingredient to our model that makes it way more realistic, something called damping.
So what is this damping force? You can think of it as a catch-all term for anything that acts like friction. It could be air resistance pushing against the weight, maybe even friction inside the metal of the spring itself. Its one and only job is to fight the motion and suck energy out of the system.
So, to get this into our math, we just add one more piece to our equation. See that new term in the middle, the a dx dt? That's our damping force. And just like before, where d squared x dt squared meant acceleration, this dx dt is just the math speak for velocity. So what we're saying here is that the damping force is proportional to the velocity. The faster the thing moves, the harder friction pushes back. With this one little tweak, our model is suddenly so much closer to reality.
And whoa, look at the difference that one term makes. Look at this graph. The waves start out big and strong, but then they get smaller and smaller and smaller until they just flatten out completely. That, right there, is the damping force in action, just bleeding the energy away until the motion stops.
Okay, so here's where it gets really interesting. It turns out that not all damping is the same. I mean, depending on how strong that friction is compared to the mass and the springiness, you get three totally different ways for the system to come to a stop.
It really all boils down to a fight between the damping force and the spring's restoring force. And this little chunk of math you see on the screen, that basically tells us who wins the fight. If the damping, that's A, is pretty small, then the spring's natural desire to bounce wins out, and we get those fading waves we just saw. But if the damping is super strong, friction wins, and the system does something completely different, no bouncing at all. And then there's this perfect balancing point, right in the middle, called critical damping.
So let's really see the difference side by side. On the left, you've got those damped oscillations. The mass still wiggles back and forth as it dies down. But look at the right. That's the over-damped case.
Here, the friction is so powerful that the mass doesn't even get one bounce in. It just slowly and smoothly oozes back to its starting point. You know a perfect example of this? A good automatic door closer, the kind that makes sure a heavy door doesn't slam shut.
All right, let's bring this all home. In our last section, we're going to see how this all connects back to the world around us, because I promise this is way more than just a math problem.
So, what's the big takeaway from all this? First, we've seen just how incredibly powerful these equations are at describing the real physical world. And think about it. Just by adding one single term for damping, we went from a fantasy of perpetual motion to a perfect model of how things actually work. And this is not just theory. This is absolutely critical for engineers who are designing everything from the suspension in your car to buildings that can withstand earthquakes. In all those cases, understanding and controlling these vibrations is a huge deal for safety and performance.
And you know what's truly mind-blowing? This exact same mathematical equation doesn't just work for springs. It perfectly describes how electricity flows in a circuit, and tons of other things. So it leaves you with this final thought. Now that you know what to look for, this pattern of something vibrating and then settling back to stillness, where else in the world around you can you see it happening? Thanks for joining me.